At the end of our last class, I and T equivalent circuits for our transformers. So I'm just going to draw those up again. So we can take a transformer. I1 and V1. Here's our secondary side with L2 dot on top. I2 is flowing into the dot. V2 is like so. And I said that we could turn this into either a T equivalent circuit or a pi equivalent circuit. So just really quickly up here, our T equivalent circuit looks like the letter T. Let's call this LX, LY, and LZ, where this is our voltage V1, our current I1, our voltage V2, our current I2, and LX was L1 minus M, LY, excuse me, that shouldn't be an equal, oh, it should be an equal sign, is L2. Our pi equivalent circuit was going to look something like this. Here's LC, LB, LA, and we said that LA was L1, L2, M was L1, L2 minus M squared over L2 minus M, and L2 minus M squared. So, and I believe I mentioned derived with two dotted terminals and the dots on the same side. That's if either one of those currents, but just one, is flowing in the opposite direction, or the dots are on opposite sides. We simply replace M with negative M. So let's say that we have the following circuit. (50 ∠0 volts. Here are our terminals. Adjacent dome coil, dot on bottom. Ohms. (20 ohm resistor over which we're trying to find this output voltage V out. like so. So this is our circuit of interest. And what in order to simplify this into something to where we don't need to wind up setting up a system of equations, okay? So for the intents and purposes of our transformer, is D. And just while I'm at it, A, B, C, and D, because this is the model that we're going to be using. So since my dots are on everywhere we have M, we replace it with minus M, okay? So what we should wind up getting is something that looks like this. So here's my 50 angle 0 degrees volts. Four ohms. Here's terminal A. We're going to have some inductance, some inductance, some inductance. C. (20 ohm) over which we're taking V out. This is our new circuit. Okay. So effectively, I've just from the terminals, connect the equivalent network, call it a day. Once we plug in what our values for. So this inductance right here is Lx, right? So what value should this have?
L1 minus.
Right? So L1 was 6 minus -4. So we'll have up here. This inductance right here is Ly. So that's going to be L2 plus M because the dots are on opposite sides. So 8 plus 4 is 12. And then down here is just going to go -M or -J4 ohms. Now, we've got a gnarly-ish looking circuit, but it no longer has a transformer or any mutual inductances or anything like that that we have to worry about. So we can really just throw simple, good old steady state sinusoidal circuit analysis techniques at, right? So no question. So somebody hit yes, KVL. KVL. Okay. Elaborate, please. I mean, we could do mesh, but that would involve us setting up a system of equations and solving that system of equations. Right? We could have just set up a system of equations with the original damn day. So how can we do this without using mesh? So we could do the equivalent impedance. So we could see the impedance seen by this 50 angle 0, which will give us this current. Then we could do KVL around this outside loop to figure out what the current I2 is, and then, or the current around this outside loop, and then use Ohm's law. That's absolutely one way to do it. Not the way that I would do it, but it is one way to do it. No, you don't have to take back the death. When I teach circuits 1 is viewing series impedances as a single equivalent impedance, right? So I would argue that if we treat this as a single equivalent impedance looking like 20, and this is a single equivalent impedance looking like 10, voltage in our circuit is at this node. So I can actually just write a single Kirchhoff's current law expression to get this voltage. Which to me seems like a little bit than finding the input impedance to find the current to then find this current. It's like one less step, but it is less steps. So I'm all about efficiency. So nothing remotely wrong with willing to do because I'm very lazy. Okay. I'm just going to call, for the sake of argument, this voltage Vx. X minus 50 angle 0 degrees volts divided by this impedance here. Over 10 minus J4 ohms plus Vx over 20 plus J12 ohms is equal to 0. And then I'm going to solve the multiplied by 1 over 4 plus J8 plus 1 over 12 will be equal to 50 angle 0 degrees volts divided by 4 plus J8 ohms. And now we have something that we can easily throw into our calculator and figure out. Everybody follow my algebra here, or so it is this current plus this current plus this current, Kirchhoff's current law, where I'm treating this bottommost node as kind of a angle 0 divided by 4 plus 8i, storing that as x 1 over 4 plus 8 plus 1 over 10 minus 4i plus 1 over x divided by y gives me a voltage of Vx is equal to 28.833 with an angle of, oh geez, if I'm in radians mode, give me a second here. Times 180 over pi. Negative 36,582 degrees volts. And then from here, V out is just going to be Vx times, let's see here, 20 over 20 plus J8. No, sorry, 20 over 20 plus J12. Which I get to be 24 angle of the answer times 180 over pi, negative 67.545. I'm turning my calculator back to degree mode like a sane person. So arguably difficult, not really super difficult. Circuit 3 problem and turn it into a circuit 1 problem. Do with this GFE1 circuit is use it to be able to calculate the amount of energy stored in the transformer. Okay, so starting again with our simple transformer model. One of T. Here's L2. Realizing that this is equivalent to following network. Sorry, I need to put the M here. Where we're defining our current I1 flowing in and I2 flowing in. By the way, everything that we're going to be deriving is using this expression here, where both currents need to either be flowing into the dots or out of the dots. And the dots need to be on the same side. If either one of the currents changes direction or the dots change direction, once again, we'll just replace M with minus F. So get used to that. We're just looking for the energy absorbed by all three of these inductors and then adding them together because that's going to be the total energy stored by our transformer, right? So the energy stored by our transformer as a function of time is going to look like 1/2 times L1 squared. So that's from our first term. Then we're going to have 1/2 times our current I2 of t squared. That's term I1 plus I2. I1 of t plus I squared. We can split some things up here, right? 1/2 L1 I1 squared plus 1/2 L2 I2 squared minus 1/2 plus 1/2 M I1. Sorry, I forgot the function of time thing there. Plus 1/2, and because I'm running out of room, sorry, not 1/2 here. I1 I2. Because the 1/2 times the 2 when we FOIL. So we have a negative 1/2 M squared here and a positive 1/2 M I1 squared here. 1/2 M I2 squared. Let's get rid of that. Is 1/2 L1 squared plus M times I1 times I2. So this is our energy stored in a transformer. Once again, if either current is flowing in the opposite direction, or our dots are on opposite sides, they're flowing into the end dot, leave it alone. But if only one of them changes direction, or it's the thing that it's this. Yeah. Right. So if we flip this whole thing over, the currents are still flowing into the dotted terminal, so it's satisfied. If we change the direction on one of these, it's effectively the exact same thing as changing which side the dot is on. Yes. Look at the dot. Yeah, so let's go back here and look if, you know, like what would a pop. This is just a let's see what happens kind of thing. We would have whatsoever, right? In fact, if I saw this, what I would wind up doing is a delta Y transformation on this thing, which would actually give me the T equivalent circuit, right? So for this particular thing, it didn't work out particularly well, but there T seems to be the one that's used a little bit more. Just for a heads up as to what's coming when we get into our electronics. Also T and always use the T equivalent circuit. Pi model just doesn't sit right with me for whatever reason. Nothing wrong with it. I just prefer this one. It just puts things in series. Okay. Stored. A lot of head shake. Okay. Looks like we're going to be doing ideal transformers on Monday. All right. We have the circuit. In the time domain. Is 12 cosine 120 pi t plus 60 degrees. That subscript T is transformer energy. T is equal to 0 seconds, just to make the math slightly less term. Expression up here. We are going to need to know canceled each other out. The only thing that we're going to wind up doing is replacing M with negative M, because everything else literally would have wound up going away. All right, looking at this equation, because it's in terms of L1, L2, and M, and we already have L1, L2, and M. I'm having a brain fart here because this seems too easy. We'll go with it. If I need to fix things, I'll just fix them later. So in the frequency domain, and I'm going to circuit, the T equivalent circuit for the frequency domain here, we're going to have 12 angle 60 degrees. Volts. an inductor here, an inductor here, and a 10 ohm resistor here. Our angular frequency of 6 millihenries, 10 millihenries, and 30 millihenries respectively. We wind up getting impedances of over here. It's going to be J108. That is not 108. My apologies. And negative J 18 pi over 25 ohms down here. Circuit, recognizing that my dots are on opposite sides. Millihenries times 120 pi, I should get this number. If I do 36 millihenries times 120 pi, I should get this number. All aware of where those are coming from. Nathaniel, did I screw anything up, or are you just playing with your phone? Okay. Which thing can't you see? So J 48 pi over 25. Okay. And then it's 108 pi over 25 on the right and 18 pi over 25 on the bottom. All right. So effectively, we just need to figure out what I1 and I2 are going to be for this particular circuit. Okay. So here's I1. This is the same exact current that would be flowing into here. Would be this current, right? So we should have the exact same current flowing around this way into the undotted terminal. So both of our currents are flowing in, but our dots are switched, which is justified our replacing M with negative M in our analysis here. Okay, so how do we find I? KCL, again, it's easy, right? If we can fix this voltages at this node, these currents should be very trivial. So once again, let's just call this thing Vx, take this current plus minus 12 angle divide 5 plus Vx divided by negative J over 25 plus Vx 10 plus over 25 pi ohms is equal to 0. Five plus J 5 pi ohms pi over 25 ohms plus 1 over 10 plus J 108 over 25 pi ohm is equal to 12 over 6 divided by 5 plus J 48 over 25 pi. Angle 60 divided by 5 plus 48 pi over 25. One over 5 plus 48 pi over 25 times I plus 1 over negative plus 1 over 10 plus 108 pi over 25 I. Store that as y. X divided by y gives me 4.813 or 1 degrees volts. So what's I1 going to be? 12 angle 60 divided. Let's throw that in my calculator real quick. So let me store that previous answer as Z. So 12 Z divided by 5 plus 48 pi over 25. With an angle of 26.06. Amps. What should I2 be? All right. Plus 108 pi over 25, excuse me. Angle positive 67.543 degrees amps. Okay. And so now That's going to look like 1/2. So L1 was 10 millihenry. I1 squared, so 1.96 cosine 0 degree. Specific point in time, so I'm going back to the time domain. And since we're finding it at t is equal to 0, the 120 pi t just looks like 0. Okay. Add to that 1/2 30 millihenries. Here's I2. So 0.286 cosine 67.543 degrees squared. Six millihenries. And then we have I1 plus I2 quantity squared. Now I believe fundamentally that I should be able to just add this expression plus this expression and then square them. Just to cover my butt, I'm going to the frequency domain first. What's your question?
Didn't the original cosine that like cosine plus have like a plus 60?
Yeah. So all of that, so that plus 60 way up here in the phase angle, it's taken care of. So again, I fundamentally believe you should get the same answer either way. But what I'm going to do really quickly is just add these numbers. So this thing plus 2.128 with an angle of 31.159 degrees amps. Fine. 31.159 degrees. Because I'm multiplying I1 times I2. I'm not adding them together anymore because of the things that canceled out. Sorry, misremembered the derivation. My bad. 1.906. This is what happens when six cosine 67.543 degrees. Close the You're 100% correct. This actually should be a minus sign because we need to be replacing plus n with minus n. So thank you for that catch. Calculator time. All right, so 0.5 times 10 times 10 to the minus 3. 1.906 cosine 0.5, 30 times 10 to the minus 3, 0.286, sine 67.543. Punching stuff into my calculator too fast and making errors. 6 times 10 to the minus 3. 1.906 cosine 60. Cosine 67.543, close. Store that as Z, X plus Y. I'm getting 13.716, no, 715 millijoules. How would you got as well? Nice. Good deal. Wanted to talk about with respect to practical transformers. So now we're going to move along to ideal. And hopefully we'll be able to finish up all this transformer business by the end of class on Monday. That being said, I'm going to put a homework assignment out today, tomorrow at the absolute latest to class meeting, what we covered in class, this class meeting. And then there will be one last homework assignment on transformers that I'll probably wind up posting sometime between Monday and Wednesday. Convolution integrals, which you guys are gonna hate. So you guys are gonna hate them because I know I hate. But it'll be okay. It's just math, just a bunch of dumb math. All right. So let's get started with ideal transformers. I've had convolution already, and so sorry, you're going to see it 2 more times in the electrical engineering program. All right. So I'm going to give you guys the diagram for an ideal transformer here. Okay. So we're going to have our voltage source, VS. Make this a phasor voltage for what it's worth. Here's L1. And out here on the right-hand side is going to be some and secondary current, I2, define my primary voltage, V1, define my primary voltage, V2 like so. Is what we call okay. Parallel lines here represent the only thing different about this diagram than our previous diagrams. 2 coils are supposedly wrapped magnetic core. Okay. So in an I have the following criterion. K is coupled coils. Another thing that we have is that the series resistance of our primary winding and the series resistance of our secondary winding Since we have perfect or perfectly coupled coils, our mutual inductance M is going to be the square root of L1. We talked about this in class, the last class. A few things today, so we're going to play around with some relationships really quick. Okay, so there is a explicit relationship between the inductance L1 and the inductance L2. Okay. The inductance of coil L2 is proportional to the number of turns in coil 2 squared, right? Which if we have a solenoidal coil, self-inductance of coil 1 should be proportional to A aptly the number of turns in coil 2 divided by the number of turns in coil 1, and that will be the same thing as the square root of L2 over L1. So A is our turns ratio. It is a unitless quantity. The behavior of currents, voltages, impedances, and even transmitted power. Well, all of these relationships over the next classroom. So, playing around with a little bit of algebra here, we should be able to see that M, which is the square, is the same as L1 times the square. So this would look like L1 squared L2 all over L1 underneath the square root sign. This square cancels out this. So anytime we see our mutual, we can actually just put it in terms L2 is just going to be A squared times L1, because that would literally be L2 divided by L1 times L1. So anytime we see L2, we can also put it just in terms of A and just in terms of L1. So let's take these relationships and let's derive some. So here's our ideal transformer. No heavy size yet. We haven't even got to the math. So here is our primary coil, dot on this side, that has N1 turns. Here is the into the dots, okay. We're going to put the dot on top. Here's our voltage V2. Current flowing into or out of the dot. What I'm thinking about having you guys is to prove that it literally does. So, choose your own adventure. I derived all 4 different permutations this morning. All get the exact same result when the dots are on the same side. All get the exact opposite result when the dots are on the opposite sides. That you guys have made. So V1 should be J omega L1 A omega M I2. Oh, I forgot an I1 here. Based on everything we've been doing for the last several days. Did I screw up any signs or anything like that? Nope. Okay. So now we're simply going to so that's going to be J omega L1 I1 minus J omega A L1 I2. And I'm going to take out a common factor of J omega L1 so that we have J omega L1 times I1 minus A I2. Over here, on the right-hand side, we're going to do the exact same thing for V2. So the positive polarity terminal of V2 is at the dot. The negative polarity, excuse me, and the current is flowing into the not dot. So we should have a negative sign, right? So negative J omega L2 I2. Is my sign correct on my self term here? So positive polarity terminal is at the dot, current is flowing into the not dot, so I believe fundamentally I should have a negative sign. Okay. Is flowing into the dot, so we should have plus J omega M times I1. L2, we're going to have negative J omega A squared L1 A L1 times I1, pulling out a common factor of J omega A L1, we are left with I1 minus A I2. So what does the ratio of V2 to V1 give us? 8. Which means for a transformer, an ideal transformer in particular, where the dots are located on the same side, the voltage on the secondary coil is just A times the voltage on the primary coil. Every time. The voltages are related to each other by the turns ratio. So if we want a step up transformer, meaning that we want our voltage on our secondary to be have more turns than coil 1. Down voltage transformer. Coil 1 could so I'm trying to decide whether to derive this myself or make you guys do it to prove. But with a negative sign. Do you want me to do it or do you guys want to do it? Yes, it would be a homework problem. You guys figure it out. It's not bad. It's literally minus I can go on. Every other part of the derivation is exactly the same. It took me, I think, 25 minutes to do it 8 times this morning. So. Okay, so sure a little bit. So I've thrown a source voltage over here. Is that our voltage source is supplying some amount of complex power to the primary winding of our transformer. And supplying it to our load. So it stands to reason that the amount of complex power primary winding has to be equal to the amount of complex power that is supplied by our secondary winding. We have no losses anywhere, so how could it be anything else, right? So power going into the primary winding has to equal. Because we're looking at this thing in the frequency domain, we could say that S1 absorbed right? So the amount of power absorbed by the primary side has to be equal to the being supplied by the secondary side. So based on what we have here, what's the amount of power absorbed by our primary side? Well, times I1 conjugate. And the amount of power supplied by our secondary side into the negative polarity terminal of the coil. So we should just have V2 times I2 conjugate. So if I took the ratio of I would simply give me V1 over V2, which is nothing more than 1 over A. Turns out these conjugate signs don't even matter because there's nothing in this system that's causing. Is that if we step up the voltage, we have to step down the current in order to maintain. Vice versa, if we step down the voltage, we have to step up the current. So let's put this in a practical context, okay? Do you think they are larger or smaller than the wires that are used to transmit power from the transformer outside of this building into this building? The long distance transmission are significant voltage way up because it means so we can use smaller and therefore transmitting power and electricity over long. Larger wires for home installation and all of that kind of good stuff, because as we step that voltage back down, the current for today, we'll look at effects on impedance and all that kind of stuff for the next class meeting, and then we'll talk about auto transformers and three-phase transformers and good stuff like that and be done.